Yeah, okay. So your first unit we have been discussing. So in your first unit we have completed nearly 5 topics, 5 lectures we have completed. So uh, first we started with the causes for the overvoltage. What is overvoltage we have started. Its causes we have discussed. Next, in that there will be two causes, internal and external. Okay. So in that external, the main thing is lightning. So we started with the lightning theories. Okay. Then the lightning mechanism we have discussed. Okay. Next we switched over to the internal cause, which is nothing but your switching over voltage. Okay. Over voltage caused by switching in your circuits. And in last class we have seen about corona and its effects. So in today's class, what we'll be dealing is we'll be dealing with the traveling waves and Bewley lattice diagram. Okay. So the same topic entirely will be studying in your power system transients in this semester itself. So if you're studying this one single question itself, you can attend in both the subjects. So this lecture six from this lecture six, Bewley lattice diagram is a 10% question we can expect. Okay. So we'll be starting with the lecture 6. So in this, we'll be seeing about traveling waves. So traveling waves is basically what you have seen in your T&D subject. So in your T&D subject, we have derived the uh, expression for your long transmission line, right? So the same expression will be repeating over here, but you know that is the same thing will be repeating, but it's not one of an important question. The important question where it lies is in the Bewley lattice diagram. The derivation they'll be asking. It is a entirely a derivative part. Okay, I will be just showing out this traveling waves as you already studied in your T&D. So I won't be covering that much, but I have given in your PPT. Okay, so first we will be seeing out. So this is your transmission line. So as you know, your transmission line will be having distributed parameters. Okay, there are two kind of parameters, as you know. One is your distributed parameters, and another one is your lumped parameters. So about the distributed parameters and lumped parameters, also I have already in while taking TND, I have said the difference. You just if you need, you just search Google or okay. So I'll be directly going. So in distributed parameters, what is the thing is your transmission line will be separately represented with the your what you can say passive components like resistor, inductor, and capacitors. Okay. So your RLC will with the help of your RLC, your transmission line will be represented. So here, what they is giving is this R refers to your per unit length of the transmission line, resistance in the per unit length. Okay. So this L refers to the inductance in the per unit length. So as you already know, the inductance and the resistance will always be in the series. So I have told you about this in your previous lectures also. I have discussed about that. Okay. So your capacitor will be in parallel. Okay. So G refers to your conductance, leakage conductance per unit length. So here what you can see is traveling waves on transmission line. The same thing you have studied the derivation studied in the uh, T&D long transmission line. That is your what you can say your voltage will be moving out from your sending side to the receiving side. Okay, it will be moving from your sending side to your receiving side. So that's the thing. So here, while traveling with those kind of things, it will be subjected to be as a wave. Okay. So in general, if there's a current flow, means the same thing I have already told in the previous lecture. That is, if there is a current flow, means current flow is nothing but your flow of electrons. Okay. So your electrons will be flowing from positive to negative. Similar to that, your transmission line also there will be a flow of electrons. Okay, so what happened is that as per duality theory by Einstein, so your electrons will be acting as both as a particle as well as wave. Okay, so your electron has a capability to act as both wave as well as your particle. Okay, so the main stream is that so while passage of the current from one end to the other end, so the current there may be some possibility of the electrons to be acting as a wave. Okay, so it is a duality nature of the electron. So if you need further explanation over that means, you can just Google it out. Next is a classification of transmission line. This you already know, but this is a basic concept. Okay, so it's a generalized form. Okay, so lines how we can classify means lines with loss and no loss. That is your line in ideal condition. Ideal condition means there won't be any loss. So lines with loss means there will be loss. As you know, there will be I square R loss in general. So lines with distortion or distortionless. So this corresponds to a electromagnetic interference. Okay, so if there is any electromagnetic interference, there will be distortion in the line, or otherwise there won't be any kind of distortion. Okay, this occurs mainly when there is interruption between the supply line, power line as well as your communication. Okay, so next is lines with small losses. The next thing is based upon the length, line with infinite and finite length. Okay, so this everything on that will be based upon the four parameters. So what are those four parameters? Resistance, capacitance, inductance, and your conductance. Okay. So now moving on. So this equation, you might have remembered in your TND. While taking TND, I covered this entire equation. That is, so you are sending how you can represent your sending in voltage with respect to your resistance and inductance, conductance, and capacitance. Okay, so it is given in this equation. Okay, so the same equation what you have learned will be repeating over here. Okay, so that is, so with the V equal to, here the voltage drop is I into R. Okay, so if here there is a resistance in the sense means it is I into R. So that is normal Ohm's law. Okay, but here we are taking for a small change. Okay, so for the small change, if you are taking means you have to multiply with your change in the change. That is the distance change you have to multiply. Okay. For example, for 5 kilometers, if the resistance for 1 kilometer, if the resistance is 5 ohm means for 5 kilometer your resistance will be 25 ohm. Okay. Similar to that. Okay. Similar to that, you have to multiply with the distance. Okay. The same thing what you have learned. So then these are two equations. Okay. So this equation is for your voltage, and this equation is for your current. Okay. So this you can easily get by applying the KVL over this line. Okay. This diagram, if you are applying KVL means we'll be getting this line. Okay. So from this, what you are doing is you are eliminating the value of dx. So you don't need the dx. So dx is on both the sides. So either what you can do is you can take it out common, this side and this side you can take it out common, and you can just cancel it out. Okay. So then what we'll be getting is the change in voltage with respect to distance. So here it is partial derivative. Okay, this represents the partial derivative. The change in voltage with respect to distance they have given. Okay, we'll be getting these two equations. Okay, so then they will be manipulating these two equations. Okay, so from these two equations, you have to get the solution. Okay, so that is this is a refreshing part only. Okay, you just don't have to go through this entire thing. You have to know about this equation. This equation you have to know entirely. Okay, and from this equation, how you are getting this equation, you have to know. Okay, So then they will be manipulating these equations to get this equation. Okay. Generally, what they'll be doing is here first they have multiplied with, again they have multiplied with the same value. Okay, like similar to squaring. Sorry, they are multiplying with dou square by dou x square, both the right hand and your left hand side. Okay. And they'll be manipulating to get this kind of equation. So here, what they'll be doing is they'll be after this, they'll be applying the partial integral pi. Okay, so pi, and finally you'll be getting the equation as like this. Okay, so in this format you'll be getting, so there will be another one equation, that is f equal to here x minus 80. Okay, with respect to the negative sign, this equation will be getting, and with respect to your positive sign, you'll be getting this equation. So don't get confused. Okay, this is not the thing you have to see. Okay, so you just know how this equations came along. You just have to know. Okay. So after this, they'll be applying the entire thing. That is, the general form is summation of these two equations. Okay, f equal to x minus 80 is nothing but the previous equation, this equation, okay, followed by this equation. Okay, so that is here they are taking the voltage, okay, voltage in terms of your equation functions. Okay, so that is with respect to this, how they are showing your traveling and waves will be seeing. Okay. So these two equations are nothing but your wave equation. This equation is one kind of a wave equation. If you're putting and seeing a wave equation format, means your wave equation format will be like this. Okay. And next is the surge impedance. This you already know. Surge impedance, as you already know, surge impedance is equal to root of L by C, you know. Okay, so in the transmission line, what does it will be means? It is root of small l by small c. Okay, so they'll be deriving this surge impedance from this equation only. From E equal to F equal to x minus 80 only, they will be deriving this. Okay, E value they'll be putting, and they'll be taking derivative, okay, to find this. You just have to know surge impedance means it is root of L by C, and it is represented by Z naught. Okay, that alone you take it out. Okay. So next, the velocity of the wave they have given. Okay, velocity of the propagation wave. Okay, so this L represents your inductance. Okay, this L represents your inductance, and this C represents your capacitance in the transmission line. Okay. Next, what they will be doing is they will be multiplying these two, capacitance as well as your inductance. They will be multiplying. Okay, to find the velocity of the traveling wave. Okay. So LC they are multiplying. So this term and this term gets cancelled out. Okay. Then 2 pi gets cancelled out with 2 pi. So finally you'll be getting mu naught epsilon naught. Okay. So if you are considering it respect to air, means your epsilon r you can take it as 1. So your L into C value will be equal to mu naught epsilon r. Okay. So this you can represent with respect to a constant as 1 by a square. For simplicity they are using. Okay. So here what they are saying. So here they are saying it as the velocity of propagation of wave, that is from your sending end to the receiving end, is equal to the velocity of light. So here they are. It's nearly equal to an assumption. Okay, it is theoretical one. Yeah, but in practical case, it is not possible. Okay, the velocity of wave which is traveling from a receiving side, sending into the receiving end, equal to the velocity of light, means the condition here what they are giving is if the resistance of the line was not neglected. Okay, then that means you have to include the resistance of the line. Okay, the velocity of propagation of the wave would be found to be slightly less than that of the line. Okay, if you are taking with the consideration with the resistance means it won't be as far with respect to your light. Okay, it will be less than that of the light. So your velocity of light is, can anybody give the velocity of light in the chat box? Velocity of light in the chat box. Can anybody type it out? What is the velocity of light? Nobody don't know the velocity of light. Okay, fine. So the velocity of light corresponds to 3 into 10 power 8 meter per second. Okay. So that corresponds to the velocity of light. Okay. So next what they're saying is for a cable. Okay. So they're considering a cable. The dielectric material has a permittivity of R. Okay. So here if we are taking a cable means this epsilon R will be having a value. Okay. So this value gets changed. Okay. With respect to your air means your epsilon R is 1. Otherwise, or some other material, it will be it will take some value. Okay. So in your cable, with respect to your cable, your velocity will be velocity of propagation equal to velocity of light divided by root of epsilon r. Okay. This is another one. Next is the energy stored in the surge. Okay. So here, what is they'll be doing is the energy stored in traveling wave they'll be taking. So here it crosses across two parameters. One is your capacitance and another one is your inductance. These two parameters are nothing but your storage elements. Okay. So in general, what your capacitance does is it stores your voltage. Okay. So your inductor what it does is it stores your uh, current. Okay. So what happens is these two are the storage elements. So with respect to these two storage elements, what will be the traveling wave? Okay, energy. So here they are giving. So the energy across your stored in your capacitance is given as half CV square. Okay, and your energy across your inductance is half Li square. Okay, so these two you will be summing. These two will be summing, and you will be getting out to be. So this equation is got from your surge impedance. Okay, so your surge impedance is nothing but dz naught. So your z naught is equal to E by I, which is equal to root of L by C. Okay, so your E will be on your left hand side, and you will be bringing the I over here. Okay, now you have to, what you have to do is you have to square it out. Okay, if you're squaring means E becomes E square, and the square root disappears, and your I becomes squared, and your C will be moved over here. Okay, so next what you'll be doing is you will be multiplying with 1 by 2 on both sides. You'll be multiplying with 1 by 2 on both sides. So finally you'll be getting is, after doing this thing, so this half C square is equal to half Li square you'll be getting. So you have to substitute instead of half Li square, you have to substitute with half C square. So one C square you can take common out. So 1 by 2 plus 1 by 2 will be getting 1. Okay. So next is what they're saying is it is seen that half the energy of surge is stored in electrostatic field and half in electromagnetic field. This is based upon this concept. Okay. So half is stored in your electrostatic field, which is nothing but your capacitor, and other half is stored in your electromagnetic field, which is nothing but your inductor. Okay. So next we will be going into the reflection. Okay. So direction of wave. Okay. So here they are giving the direction of waves over here. So if this is the bus, okay. So here junction, what they're saying is, in general in PSA you might have studied bus. So here they have taken it as a junction. So what happen is, so if it is coming in this fashion from left to right, okay, if the wave is getting reflected, so for the reflection there is some condition, okay. So in general what we expect is, if this is the A point and if this is the B point, means your direction of the wave has to be from A to B, okay. It has to cross through this junction from A to B, but uh, sometimes the wave has the capacity to be reflected, okay. So for that some conditions are there, okay. So the main condition is, this is the thing, okay. So this is the thing. So if this condition satisfies, means your wave gets reflected, okay. So over this region your impedance value will be Z1, and after this junction your impedance value will be Z2, okay. So the voltage after the junction is Et equal to Z2 into IT, okay. This the normal Ohm's law applied after the junction, okay. But what you can see is, this is this E, okay. E is the thing which is coming into the junction, okay. But some of amount of this gets reflected. This is your ER, okay. So here what they are giving is E equal to this Z1 into I, and this ER is equal to minus of this impedance, okay. That is not minus, that is minus of Z1 into IR, that is minus of IR, that is the current flow gets in this reverse direction. So that's what you'll be getting out with the minus, okay. So in general the current will be flowing over this direction, so here also it will be flowing in this direction. You have to put KCL at this junction. So I plus IR contributes to your IT, okay. Here they might have given clearly. So what happens when a voltage, when a circuit is open circuited line fed from an infinite source? That is, what they are specifying is, if this line is open circuited, okay, if this side is open circuited, okay, there won't be any kind of current flow. But here it is fed from a infinite source, okay. So at that time what happens to your E and I? So that's what they are doing. When a voltage surge E arrives at the junction J, okay, which is on open circuit, okay, as I said, this J is on open circuit, it is reflected without a change in sign, okay. So normal reflection occurs. Then also a current surge of negative of positive sign to the incident I is reflected, so that transmitted current is 0. So it is an open circuited, okay. So here there won't be any kind of current flow or any kind of voltage. So what kind of current is entering will be reflected. So your will be getting out with your negative of I, okay. So next is the, if the line is fed from a constant voltage, so C, then as reflected voltage, so G arrives at the generator N, okay. So here what we are seeing is, the source will be taking as the surge voltage. The source for the surge voltage, you will be finding out the traveling wave and whether it is reflecting out or not. You will be seeing in such a manner. Okay. So these are the conditions. You just read it out. You will be understanding. So if I'm explaining more means you'll be get bored. You just see this and you just read with respect to this concept. Okay. So the same thing they have given with respect to your short circuit also. Okay. What happens during a short circuit? Okay. So after reflection, we'll be getting out the current value. Okay. In a short circuit, as you know, there will be excess of current flow at your junction side. Okay. So that's what they are giving. Okay. So this up to this also they won't be asking any kind of questions for your with respect to your university. So but you have to know about these points. Okay, so that only I have included everything in the slide. Okay, so what is a reflecting wave, what is a traveling wave, so those things and all you have to see. But again Maheshwari ma'am also will be taking the same thing. In PhD also you will be covering the same topics. Okay. So this is a small diagram. What happens when the waves get reflected? Okay. So this is the transition point. So you can take either take it as a T or J or the junction. Okay. So this is some basic consideration you have to take. Okay. Uh, Basic consideration you have to take. So how those waves get travel? Okay, those waves travels to the downhill. Okay, the downhill is nothing but the lower potential. Okay, here it represents the lower potential. Okay, the position of the wave at any instant is given by means of time scale at the left of the lattice diagram. So lattice diagram will be covered again afterwards. Okay. So here what they are saying is the total potential at any instant of time is the superposition of all the waves. So this is similar to your KCL. Okay. So in your KCL, what will be doing is, if there's a node means the current entering the node will be always equal to the current leaving the node. Similar to that, only this point it comes out. Okay. So the next thing is they will be including the noises also. Attenuation refers to the noises or some kind of losses. Okay. So next is the Bewlley lattice diagram. Okay. So this is the very important question. Okay. So, but this question is based upon the traveling waves only, so that only the previous uh, slides were covered. Okay. What they're saying. Okay. What is the use of this Bewlley lattice diagram and what they're saying? So that we have to first infer. So here, Mr. Bewlley, what he devised was he devised a diagram for monitoring the transmitted and reflected wave. Okay, so if there is a junction J means some amount of waves gets transmitted and some amount of waves get reflected. Okay, for that thing he devised the diagram. Okay, so next what they're saying is when a voltage surge of magnitude unity reaches a junction between two sections with surge impedances Z1 and Z1, Z2, at the same diagram. We are dealing with the same diagram. This same diagram. Okay, Z1 and Z2. then a part of A is transmitted and a part of B is reflected. So here they are dealing with the assumption. Okay, first they are starting with the assumption. So what they are saying is at the junction, okay, there for sure there will be some amount of waves transmitted and some amount of waves gets reflected back. Okay. And the next point, in traversing, that is traveling the second line, if the attenuation factor is k, then on reaching the termination at the end of the second line, its amplitude will be reduced to k into a. So here what I am saying is attenuation factor is k. So in the previous slide I have told you have to include the attenuation or the noises or the losses. Okay, so that's the k factor. So you have to include the k factor. Okay, after including it becomes k into a. Okay, so this traveling waves could be considered in 6 cases. Okay, so this corresponds to 6 cases. So two cases we have already seen with respect to the traveling wave. Okay, we have seen open-ended transmission line of surge impedance Z. So with Z, one has been after the junction J, one has been open circuited. Okay, then the second thing is short circuited. Okay, third thing is line terminated with the resistance equal to the surge impedance of the line, which is nothing but root of L by C. So what happens when it is terminated with a resistance with respect to your surge impedance? Okay. So the fourth one is line terminated with the capacitor, then terminated with an inductance. Okay. Line having a series inductor, okay. Line terminated with the transformer. So here we'll be seeing only these two cases. We won't be covering all the 7. Only these two cases alone we'll be seeing. Okay. So this is the simple diagram. Okay, analysis of an open circuit line fed from ideal source. So your source will be ideal. So ideal means the source won't be having any kind of losses and it won't be having any kind of impact. Okay, by any other quantities. Okay, so here what happened is, so this is your Bewlley lattice diagram. So in your Bewlley lattice diagram, so there will be two parallel lines. Okay, two parallel lines which are indicating your time period. Okay, two parallel lines. These two parallel lines indicates your time period. Okay, so the in general always your energy gets start from your 0 point. Okay, so from a 0 it gets started. Okay, when it is coming from one end to the other end, okay, you can take it this is a kind of a junction. Okay, you can take this as the junction 1 and this is the junction 2. So from junction 1 it is starting. So junction 1 will be having the ideal source. From junction 1 it is starting. So when hitting the junction 2 at the time period t, okay, you'll be having some kind of attenuation or losses. Okay, so that is plus k. Okay, that is plus k. So before that you won't be having any kind of attenuation or losses. It directly comes out from your ideal source. So you'll be taking out the value of plus 1. Okay, then it again get reflected and transmitted to the junction 1. Okay, so over there you'll be taking with the again another one attenuation will be taken. Okay, but what happened is when this comes out from the other thing, you have to go and check the condition of the open circuit line. So here you have to go and check this thing. Yeah. So this over here, what happened is when it is coming to the third time, you can have like that in your knowledge. When it's coming to the third time, your surge voltage becomes negative. So in general, over here you will be taking with the minus of k square. That is, during the first time it doesn't get any kind of reflection. Okay, so it get transmitted to junction 2 and you'll be getting plus k. Okay, when coming to the third point, this point you'll be getting with this k, will be going with the minus k square. Why in this sense means there you'll be getting the in open circuit your voltage at the third point will be some negative. Okay. So similarly, this gets repeated. Okay, so you'll be getting for the receiving end voltage, you'll be getting with respect to your attenuations constant or the k factor. So you'll be getting 2 into k minus this one will be adding out k minus k cube plus k5 minus k power 4. Okay, so like this it gets move on. Okay. So this is in a GP. Okay, geometric series. Okay, so you'll be applying the formula 1 minus a square the whole power n by 1 minus a 1 minus a. Okay, so that formula will be applying over here. So that you will be taking this k common out, and they'll be applying to get the values your VR equal to 2k by 1 plus k square. Okay. So this is with respect to your open circuit voltage. So this is what you have to derive. Okay, up to this you have to derive in your Bewlley lattice diagram. And there's a short circuit. There's a terminator through a resistance R condition is also there. So here what happens is when if you're taking with the R, there will be another one factor beta included. That's the only difference. Okay. So including your impedance before the junction J Z1, you have to add another one resistance which is R. So that's the condition over here. The line is terminated with resistance R means so you'll be getting with the beta value and you'll be getting the same thing if you are applying, but in excess you have to put the beta values around. Okay, so for this you'll be getting VRS in this fashion. Okay, these are the conditions. Okay, so up to this we are writing itself well and good for your Bewlley lattice diagram. So but there are 7 conditions. Okay, just go through in the book. Okay, so this is an easy topic only. You have to draw the diagram and you have to write the equations with respect to the diagram. Okay. Whereas reading in your book means it will be somewhat more clear. Okay. So, I know it will be very difficult to understand in this situation about these kind of derivation. If it is in the chalk and board means it will be easy. Okay. So from this, the possible question what they'll be asking is they might be asking about your Bewlley lattice diagram in your part B. Okay, so you can also refer your previous year question also. So in that they would have surely asked in this thing. Okay, so but you are the first batch who are writing this thing. Okay. So